Thank you very much. I will talk about computer vision and learning computer vision. Most of the learning in computer vision is concerned with recognition problems like image classification, object detection, or semantic segmentation. In our group, we are focusing more on learning more the structure of a scene, so the 3D structure especially. And I will talk today about four different topics, four different networks. The first one will be on 3D shape from single images. So it will only take a single image as input and will hallucinate the rest of the object from knowledge that it has obtained from the training data. And then the other three works will be based on two images. So optical flow, you can train a network to compute optical flow directly, and it will establish correspondences, and this will be the basis for also estimating disparities in stereo images or to do structure for motion. So if you have a monocular camera and you move it through the room and to get depth maps from these cameras. So I will start with this depth from single image, or actually not depth, but really 3D shape. We'll actually start with a network that does not give you 3D shape yet, but get some understanding of 3D shape by being trained on the task to take a single view as input and producing any other view of the object. So you see here it's a typical encoder-decoder network. It sees from a certain object, a test image, one view, and it is supposed to produce another view of the same object as output, and maybe also the depth map of that. And you specify here the view that you want to see at the output by giving here some angle. Yeah, and the idea is that it's a simple feed-forward network. The idea is that it gets here does some analysis of the input image, has there some canonical 3D representation, and from that it kind of renders the output view that you want to see. So that's the network architecture, and you can train it in a supervised manner by having pairs of views, of which you know the camera pose. And we did that, and then this is what you get. So this is the view that has been provided as input to the network, and then you see the network produces all kinds of other views of that object. Although it only sees this part of the object, it can also hallucinate the other sides of the object because it takes information from the objects it has seen during training. So of course, this object was not in the training set. And you see here in the bottom row, that's the ground truth of that kind of object. We trained it on synthetic data. There are lots of 3D models of cars that you can download on the internet, and you can train on that. So here we had always some homogeneous background. You can also put some arbitrary flicker images into the background. It still works. Maybe gets a little bit more blurry. And we also tried with some real images there. It gets some more problems because it has not seen real images during training, but you see it still gets some rough shape of the object, right? It gets a little bit more blurry here. And if I actually rotate if you produce all these different views, and you rotate the object, and it looks like you have reconstructed a 3D model. So it looks pretty much like that, although there's nothing 3D in the output here. And you also see that the network doesn't learn things by heart in this morphing here, so you can just combine the representations of two different inputs, and then you see that always this car morphs into this car, and the intermediate images that are produced are also reasonable cars in a way. So that shows that it does not just learn car parts by heart and then assembles this, but it really does some fancy recombination of the knowledge it has from the training data. We also did some explicit reconstruction of 3D models. So you see that here. So we have, that's the view that I've just shown, so it renders a RGB image, but we also render the depth map of a certain view, and if you just generate all the depth maps from various views, then you get a point cloud, and then you can put that into some standard fusion method to get some mesh. Yeah, that's what we did here, and then you actually have some explicit 3D model that you can reconstruct from this single input image. And you see here a couple of examples. Again, here's the ground truth, this is the prediction, and yeah, it works reasonably. Of course, details are missing, so the network is not generalizing so well that it can reproduce the details of the cars. Of course. No, we only present these two views. So two images from two different views, and you know the view of the output image. So that's what you provide during training. So here we didn't have any 3D during training, but there have been some works where they also directly predict voxel grids, so they directly predict 3D shapes. The problem with that is that if you have this voxel grid representation, that it gets very big if you increase the resolution. So most of these results are only at 32 cube images, where you don't see many details, and that's why it's also hard to figure out whether the methods are actually good or not. So our actual goal is to really produce 3D shapes directly. And what we did for that is we created a network that can produce octree structures. So octrees are an efficient way to represent 3D shapes, because actually this voxel grid has a lot of empty space. So you actually just want to store the areas where the shape is, so the surface of the object, and not all the empty air around it, and also not the parts within the object. And an octree can efficiently do that by having only a high resolution at those points where it matters. And yeah, we provide a network that can not only generate the output shape, so the voxel grid, but also generates the octree structure that efficiently captures this shape. And you see here one of the modules that you can put into any decoder network as one layer here. So it gets some propagated features from the previous layer. And you see already the white ones, these are the ones we don't want to refine any further, so they are already finished. And the green ones, these are the ones you want to refine, that you want to have at a higher resolution because the surface is in these areas. And then you're actually here. Now you have to decide which of those you refine further. And for that, you train a classifier on the loss of some, again, in a supervised way, on the loss of some ground truth data. And then it basically classifies whether this voxel is either empty, so it's outside the object, inside the object, or whether it's near the surface, and then you have to refine these again. So this goes then into the next layer where you propagate these red pixels here, and then you do the next refinement step. So this is a module that you can just plug into each voxel generating network to save memory. And in order to really save memory, of course, you cannot store the feature maps as tensors, but you have to use some hash functions to really have a sparse representation here, and that's what we did. Yeah, so use some hash functions to store the feature maps. Okay, and then you see it scales much better than these dense voxel grids. Yeah, so if you have 32 cube, then it's not a problem. You can also use a voxel grid, but as soon as you go to 256 or 512, then this doesn't fit into memory at one point. Yeah, so you need 80 gigabyte of GPU memory to train a network with 512 cube, even if you use batch size 1 and so on. Yeah, so this is a bit restrictive. And the same with the training time. So iteration time in seconds goes up if you have these huge voxel grids. And with the octrees, you actually have a much better scaling here. Yeah, so the increases between quadratic and linear depending on the shape that you need to predict, because of course if you have a cube, for example, yeah, you can just represent it by a single octree entry and then you're done. But if you have more complex objects, of course the size goes up with the resolution. And here I now show that you can extend this 3D reconstruction from a single image to now really a 3D reconstruction, 3D shape. This is now using this octree representation, so the network directly generates the voxel grid with the octree, and here you see the results at different resolutions, and we can now go up to 512 cube or even more, but at one point you don't gain anything anymore because the network from the training data it has seen cannot capture more details. So you can really see on how much you get from your training data and your prediction algorithm, and you're no longer bound by the resolution of your voxel grid. Here you see the ground truth car. And you can even go much higher. So this is now representing whole scenes. And you see if you represent them in 64 cube, then you don't see much. If you go to 128 cube, it's still not very good. So you need much higher resolutions if you want to explicitly represent shapes in whole scenes. With 512 cube, you can get a good representation. Okay, I'll now come to the parts that use two images. So this so far has just used a single image as input. And a couple of years ago, we introduced this flow net, which estimates optical flow directly as a conv net. So you get here, you put these two input frames from a video as input, just in a stacked manner. And then you have some analysis part here, some bottleneck, and then you directly output the optical flow field at the end. So all in one step. Now the question is, does that work? Yeah, so can networks learn to find correspondences between images? Yeah, this is a learning task that is very different from classification. There you don't need to establish correspondences, but you have to find features that allow you to provide a certain class label. This is a learning task that is very different from that. The other problem is that you need training data for that. So for classification, you can use some students to annotate images, and it actually doesn't take so long because it's just a single label per image, so that's quite fine. But if you have optical flow estimation, you cannot just put someone and say which pixel goes to which pixel in the other frame. So humans actually cannot even tell for sure what would be the correct flow field. And for that reason, there are also not very large data sets available. Yeah, so there's Middlebury, where they used some tricks with fluorescent markers and so on to have 8 samples with ground truth. There's Kitty, where they use a laser scanner on a car, and then they get ground truth optical flow, but only if there's nothing moving in the scene, so they can only do it for static scenes. And then there's Sintel, which is a synthetic open source movie, and then they used the data from that. But even there, the number of labeled frames is quite small for network training. What we actually wanted to have is something like in the order of 10,000 or 20,000 training images. So what we do is, we say realism is overrated and generated some really simplistic data with motion in it. So we just called the flying chairs data set. You see here a few examples. So we just used some random flicker image, put some affine transformation on it, and then had some chairs with segmentation. So we could also just paste them into the image and then move them from one image to the next, also with some affine transformation. And that's how it looks. And because you generate the scenes, you know exactly the ground truth optical flow, and you can train the network on that data. Of course, the interesting part is on how well this generalizes. We later introduced something a little bit more fancy where we really do 3D rendering. So we created some scene here with moving cars, and then you render not only the output, but also the optical flow field, the depth map, and so on via the Blender engine. Yeah, so basically, you're hacking the Blender engine and not only producing the images, but also the ground truth that you need. And since you have full knowledge about the scene, it's relatively easy to do. You can also produce segmentation, disparate change, whatever you want. Of course, there's some extra effort. So either you have to model the scene, which is work, or you get some open source movie where someone else has done it for you, or some computer game. Or you, again, have some randomized scene generation in a procedural way. That's what you see here. That's now flying things 3D. So they are really flying in 3D space in comparison to these chairs that we have seen before. And then you can train on that data. That, of course, with that you can create as much data as you like, but it's not super realistic again. So the interesting question is now, does that channelize? So does the network that learns on this data to compute optical flow, can it also compute optical flow on scenes that don't look like this? And we tested it here on the Sintel data set. And you see that the FlowNet produces some reasonable flow. As we had two different versions here, a simple one and one with a correlation layer in it. Doesn't matter at that point. You see both of them produce some reasonable optical flow. And this, although the network has only seen these flying chairs during training. So it hasn't seen any 3D objects, apples, and so on. So it cannot learn the structures by heart. It really has to learn the matching between the two images, and that's what it has done. But it's not perfect yet. So we found out that on some data sets where some action recognition people are interested in, so this is some action recognition data set where you have rather small displacements, and where there are also compression artifacts and so on, the FlowNet didn't perform super well. I mean, it doesn't fail completely, but if you compare it to some variational method, then you see, so that's the motion here between these frames, then you see this looks much more reasonable than that. And a test that is very easy to do is you take the same image twice and you compute the optical flow between them, and with a variational method, of course, you get the correct zero flow field because that's what you use for initialization. And I mean, it isn't that bad as it looks now, so we amplified the optical flow vectors here, but you see it doesn't produce the zero flow field, but hallucinates some motion where there's actually no motion because it's exactly the same image. So we developed two ways on how to elaborate on that. The first one is to use some self-supervised transfer learning. So basically what you have here is the FlowNet again. So this is the encoder and this is the decoder, and you have the usual supervised loss on the synthetic data here. And then we have an additional task, which is next frame prediction. And for that you can train in a self-supervised manner because you just take a video and you take two successive frames, and then you have automatically your ground truth for this task. So this can be trained in a self-supervised way on the real data. Yeah, and of course, if you have real data, you don't have this loss because, you don't have the ground truth for this data. So you can mix synthetic data and real data, and if you have the real data, you only have the next frame prediction. And the hope is that this joint encoder here will then learn some reasonable features that will also help the optical flow estimation to be better on the real images. Okay. And you can apply that, and you see that this is again images from this UCF data set that didn't work very well. You see here the results of the original FlowNet, which are pretty noisy. And now if you add this self-supervised next frame prediction task here, then results get much better. So it depends a bit on the ratio between the synthetic data, the supervised data, and the self-supervised one. So here we take 9 parts of synthetic data and 1 part real data. And you see here different ratios, and you see it's relatively stable. If you have too little synthetic data with ground truth optical flow, then results get worse again. And if you have too little, then they're also worse. So somewhere here is the optimum mixture between synthetic data with optical flow ground truth and real data without that ground truth. And you can also try to measure and quantify the improvements. There's only one data set where you can do that. That's this Kitty data set, which is from the driving car with a laser scanner on top that I mentioned earlier. For that, you have real images and ground truth optical flow. And with the original FlowNet, you get this error. And if you add the next frame prediction, then you get a little increase. Of course, it depends a bit on what kind of data you do this next frame prediction. The closer it is to the data of your test data, of course, it should also get better, and that's indeed the case. So if you take frames from Kitty, then you can further reduce the error, and if you use both, that gets even better. For comparison, we also have here the FlowNet that has been fine-tuned on the ground truth optical flow that is available on Kitty. So there are 2 Kitty versions, so you can use one for testing and one for training. And it gets close to that, so that's actually quite good. And if you fine-tune the FlowNet on this Kitty data, and then you use additionally this next frame prediction, then you can again improve results. So this self-supervised task really helps to adapt the network to these real images. Another way to evaluate that is to go into an application domain. So if you're interested in action recognition and you need some optical flow as input, then you can use the action classification performance to evaluate also your optical flow. So basically it's the same action classification network with two different flows as input, and then you can see here the accuracy and action recognition, and there is quite some large improvement here on two action classification data sets if you use this self-supervised learning on top. The other strategy was FlowNet 2, and here we just refined the old architecture. So we had a couple of changes. One was improved data and training schedule, so we used this 3D rendered data additionally for training, so that also helps, and we also had a learning schedule to start with the flying chairs and then adding this other 3D data. And the other one was stacking of networks using the motion compensation. So this is basically one of the classical flow nets. Now you can just stack another flow net on top of it and use motion compensation of that from this previous network, so that this new network can focus on the still remaining error at that point. Yeah, and you can repeat the stacking at one point. It doesn't help much further. And the third part is that because these small displacements were the biggest problem, we designed some particular small displacement network, which is also trained on specific data that was rendered with small displacements, and you can then combine these two streams, and then you get some better optical flow. And yeah, here you see the improvement of that. So this is the old FlowNet, and this is now the FlowNet 2. You see it, you get much cleaner results. So this is now competitive with the state-of-the-art optical flow estimation. And it's much, much faster than all the variational methods, which take multiple seconds. So here you get results in the millisecond range. Oh. So especially the speed accuracy trade-off is much, much better. We also have different versions. So this is the full version, which runs at 8 frames per second. You also have a version with 30 frames per second or 140 frames per second. And you see the quality is decreasing a bit, but so you can play a little bit if you want to focus more on quality or on speed. You see that here. So this is a graph that has the accuracy or the error. Yeah, so this area is better, smaller error, and runtime trade-off. So also this is better here, smaller runtime. And here are these new flow nets. These were the old ones, and you see here a couple of other methods. So this was a state-of-the-art method, and you see you basically get the same error, but at 2 orders of magnitude faster speed. I mean, it's on the GPU, this is on the CPU, but still you don't get that speed up so easily by putting things on the GPU, especially when the methods are quite complicated and have some matching and so on involved. So we get a really good trade-off between speed and accuracy. You can use the same concept here also for disparity estimation. It's actually a simplified problem because in disparity estimation you have stereo images, and so there's some epipolar geometry. The correspondences in the second image always have to be on the epipolar line, so it becomes a 1D search problem instead of a 2D search problem. And this makes the whole thing just a bit easier and results correspondingly a bit better. So it's hard to distinguish the estimation from the ground truth here. So you get pretty good disparity maps. So it's just a straightforward application of the FlowNet. And here on some real data, so also here it generalizes to real data. So I will now come to the last one, which is this depth and motion network, which does end-to-end structure for motion learning. So this is a bit more complicated. So you get 2 frames as input, so like an optical flow estimation, and the network is supposed to produce the depth map from these 2 frames and the ego motion of the camera, so on how you move the camera between the 2 frames. And the problem here is that these 2 tasks are mutually dependent. So actually you need to estimate the ego motion before you can derive the depth map from the correspondences. And that makes the training of the network more complicated, so it doesn't learn things immediately. A straightforward idea that we tried and everyone would have tried, is to just use this encoder-decoder network for the depth prediction. And yeah, you would then use the features from the bottleneck and put some fully connected network on top to get the ego motion, and then combine this here, and yeah, and then train the network on some loss on the ego motion and the depth map. And we did that, and it also produced reasonable depth maps. Ego motion was not so good, and we checked what the network did, and we figured out that you can just make the second image black and it doesn't change anything in the result. So the network just ignored completely the second image. Yeah, and this is a typical problem that to minimize the training error, you don't need to learn the actual concept. And the concept is to learn the motion from these two images. But on the training data, I mean, we had that yesterday in the talk, that there are multiple global minima and you just have to pick one, but it's not sure if this one is the one that also generalizes to new data sets. And that's the point here. We want to learn the concept of structure for motion, and we are not happy by just learning the training data by heart. Yeah, so the motion parallax here was not learned at all. So this approach didn't work, and we had to put a little bit more structure into the network by forcing it to compute optical flow. So we already had FlowNet, so it was a good idea to just force the network from these two images to first compute some optical flow, so then it's forced to use the correspondences, and only then it is allowed to estimate the depth and the ego motion. Now it has already some idea of the motion parallax. Yeah, and that's the main idea here. We also iterate these networks, so it's again some stacking. So we first have some bootstrap net that basically uses these two encoder decoders, and then we have some iteration of basically the same network structure 3 times to refine the depth maps and the ego motion, and then we have some final refinement net to also increase the resolution of the final output. Yeah, and here you see how that works, this iterative process. So here are the two images, and here you see the optical flow ground truth, and here the depth ground truth. So we trained that on images from the Kinect camera, for which you get the depth map. And then that's the first prediction of the optical flow network. You see it's not super good yet, but it coarsely captures the motion, and that's quite important already to estimate the ego motion of the camera. That's the first estimated depth that you get. Now you iterate this and you see that the optical flow and the depth map get more and more refined, and that's the final step where you then get the final result. This is to show that using 2 images is really a good idea, and it generalizes better to new scenes than if you do depth from single image. Yeah, so Eigen and Fergus, they had some work on depth from single image. So it was trained on NYU data. So you have this Kinect camera, which gives you ground truth depth maps, and then you can just learn to produce depth maps from RGB images. The problem is this Kinect camera only works indoor, so the whole training is restricted to indoor scenes. So if you go outside, then the network cannot use its domain knowledge anymore. I mean, it fails reasonably. So this is now some outdoor image, and you see the shape from texture still works, so the ground is still quite okay. But you see here in the background, what you get here is not really good. Whereas the daemon is using the motion parallax, and that's why it can actually produce good depth maps and generalize to arbitrary scenes, even those that it hasn't seen during training. Of course, the priors that are in the training data cannot be used if you go to a different domain, but at least the concept of the motion parallax can be transferred in the same way as the shape from texture queue can be transferred to new scenes. You see that even better if you look at the point cloud. So this is the ground truth point cloud. And this is now the point cloud produced by Daemon. And yeah, it's relatively accurate because of the use of the motion parallax. And this is the point cloud that you get with depth from single image. Here's another example. This is now a scene from an indoor scene, which is actually good for for this method, but even there you see there's some carpet here and it's mixed up with a table, and that's why the method here is confused and produces the wrong depth for the carpet, whereas here the network also uses the motion parallax, and then it's clear that the carpet has a different depth than a table. So again, you see here the ground truth. Then the Demon method, it even looks better because it's denser than the ground truth, but don't get confused by that. And then this is Eigen's method, which is also good for just a single image, but you see there are quite some distortions here. Yeah, you can also generalize to new scenarios. So here the camera model actually doesn't really fit, and also Demon hasn't seen streets during training. So this is now a different setting. And you see the depth map is also not perfect. It's flickering a bit, but it has learned the concept of depth prediction from two images. Of course, you also can get the camera trajectory. The camera trajectory, of course, has drift because this is just based on 2 frames. So you're basically concatenating the pose of these different frames, and then you gather some drift after a while. So all the good structure from motion methods all use multiple frames and some error correction. We still have to do that here. But you see that apart from this drift, it's quite reasonable here what you get. A big advantage over classical methods is that the method doesn't degenerate if the baseline gets smaller. Yeah? So if you move the camera only a little, then these classical methods don't have enough change in the image structure to compute the depth. And this still works quite well. So here you have the largest baseline. So here there's quite some difference between the viewpoint. You get this depth map. If you now move the cameras a bit closer, the depth map doesn't change much. And even if you choose the second image to be identical to the first image, then it basically falls down to this depth from single image method. So it still produces some reasonable depth map, and whereas the classical method would just output out of memory or something like that. So it wouldn't work at all. Yeah. So you have advantages in these degenerate cases here. Also, you don't have problems with reflections, so because you don't explicitly compute point correspondences. I mean, this optical flow network does that in a sense, but the network can also learn to deal with outliers. Okay, so that's my summary. So my conclusion is that learning 3D vision is promising. So we can even do a bit more. So maybe having a full structure motion pipeline, full mapping pipeline. And I think this is also interesting for control applications. Yeah, so like navigation, robotics, and so on, where 3D vision can be quite important, and we will try to fit these networks into these control scenarios. Thank you. Yep.
One question about at the end. I was wondering how much, I couldn't quite tell on your figure, how much of the architecture was shared amongst the different tasks you were predicting? So you're predicting like ego motion and depth and disparity and flow. Is that all common architecture, or are they different?
It's the same architecture, but it's not sharing weights. Wait, I see it. So so each encoder-decoder here is a separate encoder-decoder. Only this one is now shared, so it's iterated 3 times. So this is a recurrent part here. And all these networks that you see here are separate networks with separate weights.
Did you consider having shared weights at some point? I mean, a lot of this, I would imagine a lot of the information would be representations you learn be useful across the task.
I mean, probably this network is also using features from here. We don't have a skip connection here, but you already have this motion compensation. And so what I've shown for this FlowNet 2, where we're stacking multiple FlowNets, that's not necessary here anymore because you already have a stacking here. So in that sense, we are already saving parameters compared to this FlowNet 2. But some kind of stacking is useful. So we also tried in this FlowNet 2 version. Where is it? No. We also tried to have here, instead of stacking, some recurrent architecture. and it was considerably worse. So it's really helpful to learn new parameters because the task is different. So here you have the motion compensated image and you have to reduce the remaining error, whereas here you get 2 images and you are supposed to estimate a large displacement flow field. So these are 2 different tasks, and if you have separate weights, it helps.
So if you would not take 2 images, but go a bit further into the future, so would this be helpful, or have you played with this?
We're currently working on some multi-frame version where you have more than 2 images, or like a sequence of 5 or 10 images, and see if I would expect that you get better performance, especially when you have heavy occlusions. So for example, if you have plants that have a lot of self-occlusion, and then often you cannot do any matching because you never see a correspondence between certain points in the 2 images. But if you have multiple frames, then there will be always 2 frames where you have some correspondences.
Just could you explain a little bit? I didn't understand what kind of images do you use for the training of ego motion network, or how do you call it, daemon?
Daemon, yeah. So we also use synthetic data. So there are it's called a data set called Blend Swap, where some artists have created 3D scenes, and you can then render those. And from that, you get ground truth data. But in the case of Daemon, we noticed that it doesn't channelize pretty well if you only train on synthetic data. That's different from the FlowNet, for example. And we also used Kinect data, so NYU or other indoor data sets where you can use the Kinect camera, which always provides you with an RGB and a depth image. And then you can use that for training.
Yeah, and what's the size of the training sample?
The number of training images?
Number of images, yes.
I don't know by heart, but it was in the 10,000s.
So not millions?
Not millions, no.
Okay. Yeah, thank you.
Time for more questions still? No? Okay. Let's thank the speaker again.